Good morning, everyone. My name is Sam. I am a occupational hygiene consultant at Chem Safety and the occupational hygiene team leader. And today we're going to be doing a hierarchy of controls webinar. We'll be discussing how to use the hierarchy to help reduce exposure to workers and the workplace. And as occupational hygienists, these are some of the tools and principles we use every day while on site helping clients. So there will be a facility for you guys to ask questions. If you can type them in there, and if we get time, we'll try and answer them at the end for you guys. So what are the hierarchy of controls? You may have heard of some of them. You may have even heard of the hierarchy controls. They're pretty simple overall. It's elimination, substitution, isolation and engineering controls, administrative controls, and PPE. And we're going to go through them a lot more in specific detail as the presentation goes on. But you may have heard of some of them, and some of them are pretty self-explanatory just based off the name. As you can see here, we've got all these controls. The ones at the top are the most effective. So elimination, substitution, isolation, and engineering controls. But these are often the most expensive in terms of initial costs and time consuming to implement. But they are the most effective. Whereas down the bottom of your triangle there, administrative controls and personal protective equipment. These are cheaper and quicker to implement, but they're less effective and a lot more can go wrong with these controls. So it's always about weighing up the pros and cons of your various control options. And often you'll find that the cheaper and quicker controls, the admin and the PPE, they're used first. So you identify a problem, you get some PPE and you put in some policies and procedures in place, and that gives you time to get the capital funding to do your elimination or your engineering controls. So you often end up using more than one control. So when we're doing it, we'll recommend from the top down, so elimination and substitution if possible first before all the way down to PPE. And you may be thinking, why do we need controls? It's a few reasons. The simple answer is that it's in the Health and Safety at Work Act. So I'm sure you're all familiar with the Health and Safety at Work Act. There's a duty there imposed on persons, so people, PCBUs, under this act that require them to eliminate risks to health and safety as far as reasonably practical to do so. And if it's not reasonably practical to eliminate those risks to health and safety, to minimize those risks as far as reasonably practicable. So if you look at that minimization, that's all those controls we were looking at earlier that weren't elimination. So substitution, isolation, engineering controls, administrative controls, and finally PPE. The key word there is eliminate, because that's ideally what you want to do. Also in the general risk and workplace management controls, there's the hierarchy of control measures that outlines how you should go down that hierarchy, as I showed you earlier. And also there is a duty to review controls, which is Regulation 7 there, to maintain and make sure those control measures are effective. So onto the controls, and there's a lot of them. Elimination is probably the easiest to understand control, but the hardest to implement. So we get rid of the substance that's hazardous, and it's no longer a hazard for us to have. It's the gold standard of controls, but isn't always practical to achieve. So if it's too expensive, or you no longer have a business, it's really hard to eliminate lead from your business if you're a lead mine and your job is to mine lead. It does get used, for example, the construction industry uses a lot of elimination. So think of asbestos. When they come across a site that's doing demolition or refurbishment, they eliminate the asbestos from the site by removing it or getting it professionally removed. Another process of elimination I've come across on sites is they've decided that particular product using that hazardous substance wasn't that profitable. So because they realized it was quite hazardous to the workers, they just decided not to run that product anymore, getting rid of that dangerous solvent that they were using. You can also change the process so that the substance isn't needed anymore. Another job I went to, they used a hazardous solvent to clean an injection nozzle. They were squirting foam into these pre-sealed containers, and to clean the nozzle, they used a quite hazardous solvent. They decided to, rather than clean the nozzle all the time with a solvent, use disposable nozzles, so single use. And that that meant they no longer needed the solvent and they were able to eliminate that hazard from the workplace. Substitution, it's also a pretty common and straightforward control, and also very effective. So we use it all the time, and often in safety purposes, like we use a less flammable or explosive solvent because that does the job, because it's easier to have the less flammable things than the non-explosive things than the flammable or explosive things. Or at home, you might find that your hands react to a dishwashing liquid, so you change it to a more gentle dishwashing liquid and then don't have the reaction. So you're doing substitution all the time. It can also be changing from one form of the substance to another. Most dusts are hazardous, including wood dust. But if you are loading wooden pellets into a burner instead of using sawdust, you're significantly reducing the amount of wood dust that you breathe in. So changing to a pelletized form or a more solid form rather than a liquid form, these are substitutions that can be done, same substance but different form, and reducing the hazard overall. So here's a more worked out example of substitution. This is a real life one from one of our reports. I've just renamed the product here, but product X was what they were using, and they decided it's a bit hazardous, and we do have this product X rapid version we could use. And they asked us to determine, is it worth changing from one to the other in terms of the harm caused by them there. So you can see here in the top table, product X has heptane, methylene chloride, that's pretty bad, perchloroethylene, and some other non-hazardous things that make up the 100% of the product mix. Whereas product X, the rapid version, has aromatic hydrocarbons rather than heptanes, propanol, and carbon dioxide, and the non-hazardous makes up the rest of it. So, different materials, but unless you're a chemist and you know the hazards of all those individual substances, it can be quite difficult. Luckily, we can look at the safety data sheets, and they break things down into those hazard classes that you can see here. So product X was a 2.1.2A flammable aerosol. That was a 6.1D. It was acutely toxic on ingestion and on inhalation, irritating to the eyes, irritating to the skin. It was a known carcinogen, harmful to the nervous system, toxic to the aquatic environment and to terrestrial vertebrates. So a lot of things not great about product X, but if we just simply look at the rapid version now, it's a flammable aerosol as well. It's still toxic on inhalation and ingestion, irritating to the skin and toxic to the environment, but it's no longer a carcinogen. It's no longer harmful to the nervous system, and it's no longer irritating to the eyes. So overall, that's a win. We've substituted to a less hazardous product. So we still need controls for the new product, but they are less controls than what we needed before. So then we move on to isolation and engineering controls. This involves separating the hazardous substance by distance, time, or physical barriers. Engineering controls can also be used to achieve this, like extraction and automation. So we'll go into some better examples here. So distance is an easy one to figure, or physical barriers, we sort of have a mind on them, but also time can be used. So using time, you might have a hazardous process that creates a lot of fumes. And instead of doing it in the middle of the day where there's all the workers in the workshop, you do it right at the end of the day, you make sure it was safe, and then you close up, leave the extraction on, and come back in the morning and all the fumes have dissipated and gone through the extraction. That way your workers aren't exposed and you're isolating via time. Another example is a physical barrier, like the sand blasting booth we can see here in this picture. So there's a lot of, normally it's a garnet-based sand being blasted to abrade the product in this booth, but the worker isn't actually exposed because it's all in that enclosed space. Now, the difference between isolation and engineering controls, especially when you get to physical barriers, can be quite minor, and they can often be both at the same time. Another example of an engineering control here is an LEV system, so local exhaust ventilation. In this case, you've got two welders here. They're wearing PPE as well, as you can see, but they've got these flexible extraction hoods that suck up the fume, drawing it away from their breathing zone. And if you can see in the picture there, it's actually quite effective. A lot of the fume is going into that capture hood. So it's definitely reducing the hazard for them, and it's isolating them from the environment. It's also an engineering control. Another engineering control we have is automation. So these are some car building robots here, and therefore the people no longer have to be involved in that process, and they aren't being exposed to the hazardous substances involved. You can also see them using automation for painting, palletizing. There's a lot of processes where they are now completely run by robots. Then we have administrative controls. So these are controls that aim to change the behavior of the workers so that in order to reduce their exposure, these are things like policies, procedures, training, maintenance, and good housekeeping. It's amazing how much that if you don't go through a regular cleaning schedule, the dust and, for example, silica dust in a concrete cutting workshop builds up over time. But if you have a process where end of shift or end of week, there's a pretty thorough cleaning, you'll find that the background levels disappear, and that means that even tasks that aren't involving concrete cutting, they're not really getting that exposure anymore. Other things are setting up policies that, you need to wear this PPE or you need to be trained. All these things help reduce and they change the behavior of the worker so they're hopefully not being exposed to as many hazardous substances. And then the final control that we'll go into detail with today is personal protective equipment. So this is often the last resort of control measures. It's simple and quick to initially implement, but long-term costs to maintain an effective PPE program can be high. So unfortunately, this is often the only control we see on site, and it's the least effective. To be useful, the PPE needs to be fit for purpose. It needs to fit the worker. Most PPE is one size fits most, and as I'm sure you know, not everyone has a most sized face. So the workers need to be trained on the use and maintenance of the PPE as well. It needs to have replacement schedules because hard hats only every 3 years, or mask filters can be as little as every day. It needs to have spare parts in case bits go missing. Fit testing if you have a respirator, they all need to be actively managed going forward. So that although the initial cost can be cheap, the ongoing management of these controls can be a lot more expensive as opposed to elimination, where you have no ongoing management. You may also see the term RPE used. So this is for respiratory protective equipment, and it's a subtype of PPE. It does have some specific guidance, like the Australian and New Zealand standards on respiratory protection that involve things like fit testing, etc. But overall, the same principles apply. And at the end of the day, PPE relies upon the worker using it correctly to get the right results. And you'll find that their behavior, them not, being clean shaven or not doing up the buttons on a protective jacket or not wearing the goggles correctly, they all mean they're not getting the degree of protection that they need to do. So why do you need more than one control? Here's an example of using only one control measure. As always, the Simpsons tend to have a joke for everything. So this is radioactive man, and he's about to be hit by a whole bunch of nuclear acid or radioactive waste. And they've given him some PPE. So they've got some safety glasses. And as you can see, they weren't really protective there for what he needed. You needed multiple control measures to protect him in this situation. And the same thing occurs in real life. So there's something called the Swiss cheese model, and it's used for a lot of areas where you have multiple layers of controls in place, not just in hazard hierarchies, but in other areas as well. So no control measure apart from elimination is perfect. If you think of each control measure as a piece of Swiss cheese, each control measure has its own flaws or weak points, so the holes in the cheese. But if you have enough layers of control, then you minimize the likelihood of the weak points lining up and getting that critical accident. So you can see here, you've got your explosion and you've got all these layers of Swiss cheese, or in this case, your controls, to stop the person from being harmed at the end. So you got engineering controls. And if one of the holes was that it wasn't serviced, then there's a chance that the harm's going to get through to the person. Then you got some administrative controls. So the person wasn't trained about what to happen when an explosion happened. But finally, they were wearing PPE, so they were protected, because when you have all these holes lining up, that's when a disaster happens. But if you have enough layers, the odds of something going through all the layers is very low. So I thought we'd do a wee case study on COVID-19 in New Zealand, because it actually has a lot of controls that we use and what we're all familiar with. So if we start at the top of the hierarchy, we've got elimination. This is the aim, but it's not always possible because people want to come back into New Zealand. So we can't really effectively eliminate COVID-19 from New Zealand. It would have too many political costs for them to deem that being reasonably practical. So we can try substitution. It's not really possible with COVID-19 as it's not going away. It would be great if we could replace it with a common cold, a less hazardous virus going around, but that's just not really plausible. So we go down to the next step of the hierarchy of controls, isolation and engineering controls. So this is the managed isolation or quarantine. So we're putting people in the managed isolation for 2 weeks. They've got their ventilation systems, all that's in place to protect, isolate the virus from us so that it's not contagious when these people get released back into the general population. And then we've got administrative controls. So the COVID-19 app, the QR codes, and the alert levels. These are all administrative things that the government has put in place to try and influence our behaviour, so we know where we've been and know who we might have interacted with, or the alert levels, knowing that we can go to the grocery store, but we can only go one person at a time versus there's only 100 people in a room building at any given time to there being no limit. These are administrative controls put in by the government. And then finally, we've got PPE, so face masks, you might see all the stuff that the nurses are wearing when they take your COVID swab. And as you can see, there are multiple layers of control are present here to protect us from COVID-19. And as you can see in Australia, these don't always all work. That's why elimination is the perfect one, and then we have to make do with the rest. So it's also vaccination, that is a control. And you could argue it could be elimination if it worked and there was no way for the virus to spread, we've eliminated it. But you could also see it as an engineering control. We've come up with some device to help reduce the exposure, in this case, a vaccine. So what do you have to do once you've got all your controls in place? You've got to review your controls. So as part of any good health and safety management system, the control measures put in place need to be periodically reviewed to see if they're still effective. They also need to be reviewed whenever the process changes. So it's one thing having a set of controls that work for this process that you've been doing for a few years, but now you've got a new product that you make, and actually you use new tools, you use new equipment and new solvents in this process. The same controls might not necessarily be effective, so you need to go back to basics and start your risk reviews and go back and see if these still effective. The review could be lots of things. It could be maintenance on extraction, tuning of forklifts, or review of operating procedures. So there's a lot of things you can do to review to see that your controls are still effective. You could also do exposure monitoring, so you could see how much the workers are being exposed to, whether that be air monitoring or biological monitoring. Other controls also have specific actions that need to maintain their effectiveness. So servicing, extraction system or ventilation system should be serviced every year or so, and it should be a log of their service and what they did. Refresher training, so if people have gone on a height safety course, that should be refreshed every 2 to 5 years, depending on your policies there. Fit testing for respirators needs to be every year, or if people gain or lose 10% body weight or have dental surgery. There are a lot of set specific actions that are needed for certain control measures. And just going back to the general risk and workplace management regs, Regulation 7 is the duty to maintain effective control measures. So a PCBU that implements a control measure to eliminate or minimize risks to health and safety must ensure that the control measure is effective and maintained so that it remains effective, including by ensuring that the control measure is and continues to be fit for purpose. Fit for purpose and suitable for the nature and duration of the work. Sorry about that for the slides there. So we've come to the end of it. Does anyone have any questions they would like to ask through the chat function there? Q&A. Yeah, you can always email us and ask questions. We're more than happy to help. We're not lawyers. We don't charge the moment we pick up the phone. So yeah, any questions, feel free to contact us. There'll be a follow-up email for you guys. So for those that can't make it, there'll be a link that's sent out to you as well. And yeah, feel free to join our next webinar sometime next month. Yeah, and yeah, thank you for joining.